Okay, well, spring is finally here. A day in the 70s. Good news. From winter to summer, and now we finally get spring. Well, this is lecture 11, and this would be for the day of May 12, if we were on a regular schedule, which we're not really. Um, so let's see, we're starting chapter 7, still have 7, 8, 9, and 10 to go. We have a triple back-to-back triples in chapter 7, but that's because a couple of the sections are pretty short each time. In fact, this is going to be a shorter lecture than average. And then will be just the 2 sections per day until then. The very last one will have a review after the final section. So let's get into sampling distributions, essentially the first half of chapter 7. You read about opinion polls in newspapers, magazines, the web every day. These polls are based on sample surveys. Have you heard of sampling errors and non-sampling errors? It's good to be aware of these kind of errors when reading poll results. In fact, they will even talk about a margin of error if they're a credible poll, that is. Hopefully that error isn't too large. But sound sampling methods are essential for opinion poll results to be valid and to minimize effects of these errors. More of that material was actually covered in the beginning 2 chapters of the class, and if you're interested in that, go ahead and skim through that. It's not directly on the tests, but it's still interesting information. Okay, we'll talk about population probability distribution as compared to a sampling distribution. A good, well-taken sample can represent the population. In fact, censuses are tough to do, and samples pinch in for censuses all the time. So a population probability distribution, such as the bell-shaped curve, it's a probability distribution of the population data. And here are only 5 students in an advanced statistics class. Yeah, I've been there. 5, even less in some classes. And here are the midterm scores of these 5 students. Let X denote the score of a student. So what they've done is they've noticed that the 80 showed up a couple of times, which is fine. So we just simply put it as the frequency equaling 2. But the others only showed up once apiece. Total of 5, obviously. And by the way, this is a population, very small population, but it's not a sample. So each one of these scores, well, many of these scores showed up 1 time out of 5. So relative frequency, which is a proportion, 0.20 for 70, 78, and 95, but 0.40 for the 80 because there were 2 out of 5 there. And obviously the sum adds up to 1. And here's the table. Basically the same thing we just looked at, except a little bit more concise. And I wouldn't say this is earth-shattering. There's not very much here yet. The probability distribution of X bar, though, which it does actually have a probability distribution, and it's called its sampling distribution. It lists the various values that X bar could assume and the probability of each value of X bar. So we'd have to take a sample out of the population and look at the various types of X bars there could be. Now, of course, if you have a large population, this would be so tedious, approaching infinity, nobody would want to do it. So what we look at are very small examples, and we'll take a look at the sampling distribution based on some small examples. And so instead of 5 students, we're going to take 3 as the sample size, and so that'll be our change up. So we have 5 in the population, but only 3 in each sample. Sounds silly, but we will make a point here, and we're going to take the number of possible samples as given as 5C3. We're picking triples out of a group of 5, and it's without replacement, by the way, from that population. And when we put it into our calculator or even use the formula, we find there's 10 different ways to do that. And so what they've done is they've given each of these scores letters, and A, B, C, D, E. C and D look the same, but they are considered to be different. And then they, librarian style, kind of put it in order, arranging from A, B, C all the way up to C, D, E. And that is basically the 10 possible samples that are found. Notice the order does not matter. These are combinations, so they have just been alphabetized for your convenience. That's all. And so here's the full list of the sampling distribution. And so each group of 3 has its own list of scores that are chosen. These happen to be the bottom 3, if you rank them from lowest to highest, although it's a tie, since C and D were the same. The X bars are lowest here in the first couple of samples, 76. On the other end of the spectrum, if you pick C, D, E, those are the 3 highest scores, and that mean is 85, the highest of all. So it generally moves up as you kind of go along the list, but you see all these different values that have been rounded to 2 decimal places. And guess what? They form a distribution of their own. And this one we could actually look at because it's rather finite, rather small, but it does make a point. 76, that average shows up twice. 76.67 shows up once, etc., etc., etc. And this does continue to the next page. And the first value does have a 20% chance occurring. Then we've got 10% for the next 3. And as we go to the next page, we see a couple more. And a couple of more duplicates. The 81.67 did show up twice. 84.33 showed up twice. Each of these has a 20% chance, and the 85 only had a 10% chance. Of course, the total is exactly 10, and the sum of the frequencies is also 10, also known as capital N, I suppose. Well, actually, no, just some of the frequencies would be called N. Good enough. And here is the table that illustrates this. Some showed up more than once, and they get a little bit of a boost on the probability. And the others, they only show up one time out of the 10 possible ways, combinations, then you would have 10% for each of those. And they've ranked them in order for the X bars. So if you pick one sample, you may think that the mean is 76. You pick a different sample, you may think the mean is 85. Notice they're not that close together. So this is the part of the nature in the sampling. You can collect good samples and still be unlucky, so to speak, to miss the true mean. This year being an election year, political polls, although because of the virus you don't see so many of them now, but typically you see lots of political polls during an election year, and sometimes the pollsters are quite fortunate in that they pick a very representative sample. Other times perhaps they don't. Nothing done wrong statistically, but sometimes they're just unfortunate, and that is part of the game. And time has also got something to do with it too. The closer you get to November, usually the more accurate your poll is. A poll taken in April or May is too many months ahead of the election for it to be meaningful in November, at least usually. So now we have 2 different kinds of errors. One's called sampling error, one's called non-sampling error. Sampling error is something you can't really do anything about. That's just natural. And it's going to be the difference between the value of a sample statistic and the value of a corresponding population parameter. So what we mean by that is the X bar being your sample minus the true mu, which you probably found out later. Because if you knew it in advance, there wouldn't be much reason to do a sample. And so this typically is not 0. Ideally, in a perfect world, it would be, but usually it's not. Hopefully it's pretty small. And we assume that we have a random sample and no non-sampling error has been made. So we'll get to that in a minute. But here are the ones that you could do something about. Errors that occur. Human error. Let me put down the word human. Errors that occur in the collection, recording, and tabulation of data are called non-sampling errors. They are considered very bad. And here are some ways that they could occur. So if the sample is non-random and usually non-representative, the sample results may be too different from the census results. So if you go out as a pollster and you interview all your friends, and maybe you happen to live in Beverly Hills or someplace like that, you may get a different result than practically anywhere else, and that would not be a random sample. The questions may be phrased in such a way that they are not fully understood, such as full of triple negatives, as statistics occasionally does. Luckily, our class doesn't really do that. And it may not be understood by the members of the sample or even the population, and then you get all kinds of biased results because they don't really know what they're saying. The respondents may intentionally give false information in response to some sensitive questions. Yeah, that can happen too, especially if there's a question about AIDS or sexual habits or some other hot button issue regarding income or something like that that people really are not sure they want to answer truthfully on. And of course, the poll taker may make a mistake, enter a wrong number. Sorry, wrong number in the records, make an error while entering the data on a computer. And yeah, part of the game is as you become a statistician, which I was for a while at UCR in the Forest Service, yeah, you have to spend days sometimes entering data. Sometimes you're behind and you've got 2 or 3 days of just typing numbers in. Yeah, that's not much fun, but everybody's got to do it sometime. And yeah, after 8 hours in a row of entering data, you might have made a mistake in there somewhere. And the idea is to pay attention and try to avoid that at all costs. Reconsider the population of 5 scores given in the table. So suppose one sample of the 3 scores is selected. So we just did this, and the sample includes this particular 70, 80, and 95. Okay, so the true mean, which we find out later, is 80.6. Our sample, on the other hand, gave 81.67. Not a perfect match, but yeah, it's pretty hard to get a perfect match. And in this particular case, the sampling error, as you take the difference, is 1, a little bit over 1.07. The mean score estimated from the sample was a little bit higher than the mean score of the population, which is what the goal was. So as pollsters try to estimate the percentage of people who will vote for candidate A or candidate B, C, D, etc., or maybe propositions the same way, they can compare their latest polling data with the true election data. That's a census, actually, and they can see how close they got. And they rarely hit it right on the money, even to the nearest percent, but the idea is to be as close as possible, and they always revise their techniques based on that. So anyway, this difference occurred due to chance. We used a sample instead of the population, and this is considered acceptable. And not very bad luck, because that does seem to be pretty good within 1 unit. Now, however, if we selected the sample of 3 scores and mistakenly record the second score as 82 instead of 80, that's bad. So we put the 82 in, and that's a mistake. Doesn't seem like much of a mistake, but notice how our mean has changed. Our X bar, our estimated mean, sample mean, is now up to 82.33. So when we take a look at that versus the true mean, 80.6, we now find our overall error is 1.73. This is the error, plain and simple. However, what they're going to do here is they kind of overanalyze this for just a bit. We will take away 1.07 regarding the natural sampling error. Let me put the word natural in, because there's really nothing you can do about that. And see what your error was. That's called the non-sampling error, and that's what this slide does. So does the book, for that matter. And when you take the difference, because of the error, we got it all the way up to 1.73, but we already had kind of a natural error of 1.07, which means our particular non-sampling error, that's the bad one. I guess I should put a frowny face on it. And that would be an extra 0.66 of an error. Not good. Not good. But if you enter in millions of data points, the odds are overwhelming. You might have made 1 or 2 mistakes along the way, and hopefully they're as small as only 2 units. If somebody turns out to be 222 years old, according to your data, you probably typed the 2 button a little bit too long. And that goes into another branch of statistics we don't have time for. But sometimes I just make it as simple as just ask the boss what to do, and you have that kind of error. Anyway, here's a picture on a number line that just isn't really necessary, but it does show you how you might have expected to get that far naturally, but then that got even further away due to the non-sampling error that the person made. Okay, looking at some more examples here to kind of review. Probability distribution of a sample statistic that is formed when random samples of size n are repeatedly taken from a population gives us what they call a sampling distribution, typically of X bars. There are others as well. We'll look at p hat also later. If the sample statistics is the sample mean, then we have the sampling distribution of the sample means, as I just mentioned. And so here's a good picture here. Here we have 5 different pollsters with 5 different samplings, and they each got different answers. Now this kind of implies a y-axis here. Let's not worry about that. But person number 1 got a low X bar. Person number 5 got a pretty high X bar. That's just the way it's spread out, and every pollster will get a slightly different number. So the sampling distribution consists of the values of all of the sample means, as many as there possibly can be. We were lucky to only have 10 last time. Usually it's in the trillions or beyond. And luckily, the mean of the means is the mean. That sounds a little absurd, but it's true. If you took all the sample means that are possible and averaged them together, you'd be right back where you started. So the mean really isn't the problem here. However, the standard deviation does change. The standard deviation of the sample means, which can be figured out, is equal to the population standard deviation sigma divided by the square root of the sample size n. So notice how it's changed. We have to take n, which is greater than 1, and divide the square root of n into the sigma, and that is our new sigma of the sample means, that is. And it happens to have another name, the standard error of the mean. SEM sometimes is used for that. We don't overuse that here, but it is possible to call it that. So here's a good example of this. The number of times that only 4 people go grocery shopping in a month is given by population values 1, 3, 5, and 7. So in other words, somebody goes once a month and somebody else goes 7 times a month. And here's a probability histogram, rather simplistic. And notice, because there's only 4 people, each one of them has a 1/4 chance. 1 out of 4 is 0.25, so it's like a uniform distribution, which we didn't really cover. So we randomly choose 2 of these 4. And with replacement, by the way, so we put it back in, and the person can be rechosen. So this one's a little different than before with replacement. So list all possible samples of size 2 and calculate the mean of each. These means form the sampling distribution of the sample means. We'll take a closer look as to what's going on. And we can find the mean. Don't really care much about the variance. That's just a side topic. And standard deviation of the sample means. We can compare the results with the mean. Mu equals 4, which is kind of easy to get. Just 1 plus 3 plus 5 plus 7 divided by 4. 16 over 4 is 4. Standard deviation, well, I'm not going to go into the details, but you could find that to be the square root of 5, which is around 2.2. But you could find that out yourself. Just, for example, 1 minus 4 squared plus 3 minus 4 squared, et cetera, and that method there. But just take it for granted that 5 is the variance, but square root of 5, 2.2 is the population. And this was anyway, let's move on. Okay, so here are the 16 samples of size 2, each of these pairs from the population and the mean of each sample. So we could start all the way with 1, 1, which clearly averages 1. We can go to 1, 3, which averages at a 2. 1, 5 averages a 3. 1, 7 averages a 4. And then 3, 1, 3, 3, 3, 5, 3, 7. Notice the duplicates are allowed. It did say with replacement. Put it right back in. You could pick the same person again. Yep, that does increase the number of samples. But right now the list is not prohibitive at all. So we just continue all the way up to picking 7 twice in a row, or the X bar could be as high as 7. And so all these values between 1 and 7 are listed, and they form an interesting pattern. At least I find it interesting, because as you start to list the numbers of 1s and 2s and 3s and 4s all the way up to 7, they kind of form an interesting probability structure. The 4 showed up 4 times. Notice a 1, 7, a 3, 5, a 5, 3, and a 7, 1, all averaged 4. So it was a very popular number, showed up the most. So it is the peak of this distribution. 4 over 16 is exactly 25%. And all the others kind of formed a situation where one could even argue this is starting to become almost like a bell curve, more or less. But anyway, that was remarkable for such a small amount of data. So we can construct the sampling distribution using a probability histogram to kind of see the pattern there. And so now we can go ahead and use the formula, and the mean will not change. So once you have the mean, you're done with the mean, whether you call it mu or mu x bar. And then it turns out we don't much care about the variance, but let's go to the standard deviation. And it said divide by the square root of n. That was the square root of 2. So the standard deviation, which was already given, was square root of 5. So we took the square root of 5 divided by the square root of 2, just another way to write it, and that works out to be 1.6. It's a little bit smaller than what we saw before. It's less than 2.2, which was the basic population standard deviation. And we just repeat ourselves and see the same exact results. Going on to section 7.2 now, the mean and the standard deviation of x bar, which is what we've led into from the end of this past examples, and which kind of transition between the two. We can take a look at mu of x bar and sigma of x bar, as we started to do already. And as we've already said, a bit of a review here, the mu is the mu, period. But the standard deviation does involve taking your basic standard deviation, which sometimes is given, and we can just divide by square root of n. If n was 1, there wouldn't be a change at all, but then that wouldn't be much of a sample either. But we do have the sample size being greater than 1, and we do have this other little side note that this book uses. And if your sample divided by the population is less than 5%, we're good, because we have a small enough sample that it doesn't really bump into each other. The data doesn't really collide and form independence issues and become dependent. Well, we'll talk about this a little bit later. I will give you one example when the alternative is used, which is a bit rare, but it can be used. We'll get to that later. For now, I guess we're going to it right now. Sorry. We do have the fact that sometimes the sample over the population is actually greater than 0.05, and then everything else is the same, except we attach this new item called the finite population correction factor. Yeah, we would have to include an extra adjustment number, and we'll show you how that works in a little while. This doesn't happen very often, but it can happen, especially in your book. There is an error here. Let me cross it out right now. Your standard deviation of the sample means is always smaller than the population standard deviation, because we divide by some number that's greater than 1. The square root is still greater than 1, so it gets smaller. And so they're saying the spread is tighter. So it may start off as flat, but then we're not going to make it flat anymore. Sigma sub x bar will be a tighter situation, and it will not be spread out too much, as considering the regular flattened curve, so to speak, of just sigma from the original data. Okay, the standard deviation of the sampling distribution decreases as the sample size increases. So if n gets to be like 1,000 or 10,000 or something, then you have a really pointy looking distribution, especially if you're trying to keep the same scale. It can get pointier and pointier, but that's no big deal. N can be 4 also, and then you hardly see much of a difference at all. Okay, so let's take a look at this one. The mean wage of 5,000 employees who work at a large company is $27.50. Standard deviation is 370. X bar is the mean wage per hour of a random sample of certain employees selected from this company. Find the mean and standard deviation of X bar for a sample size of 30, 75, and 200. The mean is not a big deal. It's the standard deviation that we have to worry about. Provided we've heard that it's normal or it's 30 or more, it's a rubber stamp situation. There's nothing to calculate. It's almost like a trick question in case somebody puts something else down. Let's take a look at part A. N equals 30. 30 shows up here finally, but let's take a look at what happened here. We had a population size of 5,000, and the mean and the sigma were given before, and what we have here is a ratio of 30 to 5,000 being very small, which is usual, and this is the usual situation. So leave the mean alone, but adjust the standard deviation with respect to the sample mean by dividing your given sigma by the square root of n. So the 370 that was given earlier is now divided by the square root of 30 on your calculator, and they like to give it another decimal place, 0.676. So 67.6 cents is another way to say that. And that's less than 370. So that's the point they were trying to make before. If you're taking samples, your standard deviation shrinks, sometimes quite dramatically, which is an advantage to have a smaller spread, smaller standard deviation. So now we're going to talk about 75 in the sample size. And yeah, we're still way below the 5% threshold. No sweat. Leave the mean alone. Nothing to see here. Just leave it alone. But in the standard deviation, yes, you will have to divide by the square root of 75. And when you do that, we're down to only about 42.7 cents. It's even smaller than before. Why? Because the 75 is larger than before. Let's go to part C. Now we're up to 200. And although our sample size is starting to get a little big, it's still less than 0.05, so we're good to go on the standard formula. And so when we leave the mean alone, of course, and divide the 370 that was given for the standard deviation, and divide that by the square root of n, now we're down to even less, 0.262. What I thought I would do, as I've done in my lectures for a while, give you another example. I didn't get a blank slide in here. I should have done that. But if we put in part D and let n be something else, such as 300, then what? Well, little n, the sample size over the population size, is 300 over 5,000. That is a 0. But this is 0.06. Oops, greater than 0.05. Mean is the same. Leave it alone. But sigma will not be. We'll have to take that new formula. We'll keep the original part, which is still the biggest part of it, and make this adjustment with the correction factor, and it'll be multiplied by capital N minus little n divided by capital N minus 1 and square root that whole thing. So what happens in this particular problem is you still have your 370. N is still whatever was given, so here's square root of 300, but then this adjustment factor comes in. We take 5,000 minus 300, which I will just go ahead and tell you is 4,700. So take your big N minus your little n, and then, although it doesn't seem like it matters much, capital N minus 1, 5,000 minus 1 is 4,999. So what will happen is you get some values here. I'll go ahead and put some approximations to show you what's going on. 0.2136, which already is smaller than the 0.262 from the prior example. But then we get this correction factor that gets us an accommodation for it being not so independent anymore. And we've taken about 97% of the other value. And when we apply the correction factor, we're down to back to 3 decimal places, 0.207, which is a little less than it would have been 0.214, although they would have both rounded to 21 cents, ironically. But with extra decimals, you do actually see a difference. And if little n was like 1,000 or 2,000, then you'd really see a correction factor. Then your sample is almost becoming too big, which is kind of ironic considering we like having bigger samples. The bigger the samples, the better. But then there is an adjustment that has to be made. So there is an extra example for you. Okay, this is lecture 11, part 2, and we're on 7.3. It's the shape of the sampling distribution of x bar, also known as x bar. The shape of the sampling distribution of x bar relates to the following two cases, and the population from which the samples are drawn can be normal, or maybe it's not normal, which is an interesting concept. So if you're normal already, and we do have to tell you to assume normality, and when you do have that, then you don't have to worry about it anymore. So if the population from which the samples are drawn are normally distributed, and you have a mu and a standard deviation, then the sampling distribution of the sample mean x bar will also be normal, regardless of the sample size. Of course, n better be 2 for it to mean anything, but when it's 2 or more, you're good. Same rules apply as before. Change your sigma. And here's a picture of what happens. If you already have normality, you've got it made. Here's the basic population distribution, and it's normal. You can tell by looking. But then, if we take samples of 5, and notice we're not telling you what capital N is here, it's gotten a little bit tighter, but it's still normal. And now if N is 16, the sampling distribution of X bar is tighter yet, but of course it's still normal. I mean, if it started normal and it's getting more normal, what more can you say? Is it super normal? Notice here that N is 30 and N is 100, and all that's happening is your standard deviation is getting smaller and smaller, and everything stays normal. Here's an example. According to a physician compensation report, American internal medicine physicians earn an average of $196,000. We saw this already, but now let's say that the mean is that amount and the standard deviation is 20,000. We've seen these numbers before. Calculate the mean and standard deviation of X bar. Describe the shape of the sampling distribution when the sample size is 16, 50, and 1,000. And notice, it did say approximately normally distributed, so we don't have to worry about N. We don't have to worry about it. And later on we might, but not yet. So 16, although it's a relatively small number, is good to go right now. And so here are the calculations. We take our $20,000 that was given, and N will be something greater than 1 for us to even go here. And here we've got a perfect square, makes it pretty easy. Square root of 16 is 4. And you divide 20 by 4 to get a 5,000, and that would be your standard deviation. Notice, there's nothing to see on the mean. It just stays the same. So we have 16 physicians in a sample, and it's approximately normally distributed, although with a tighter standard deviation. And here's the picture that compares the two. From the population distribution, sigma was 20,000. If we're going to do a sampling distribution for N equals 16 and find all those X bars, it's still normal, but the sigma has changed to 5,000, a little bit tighter each time. And as we ramp it up a little bit more and have N equals 50, then although it's not a perfect square, we still get even a smaller standard deviation than before. We divided by a larger number despite its square root, so the sigma went down. This is a mistake. This is meant to be 50 such physicians, and of course it will stay normal. Once it starts normal, it's going to stay that way. But that's not the remarkable effect. The remarkable effect is that when you have non-normal data that becomes normal, it's almost like a statistical miracle. But we'll get to that in a minute. So notice how this one's even tighter than before. When we have N equals 50 for our sampling distribution, we have a tighter, smaller sigma. A little bit more precise, not so bad. Sort of a reward for getting a bigger sample. And the part C, if we have N equals 1,000, now our standard deviation is much smaller, down to only about $600 something. And once again, another mistake. They meant to say 1,000 such physicians for the samples, and they will stay normal, of course. And a much tighter distribution, and they're trying to draw it to scale basically, but for sample sizes of 1,000, we have $632.46, let's say, or the standard deviation with regards to the X bar for that such huge sample. The central limit theorem is a very big theorem in statistics. I've spent many lectures trying to describe it in layman's terms, and we luckily don't have to do that so much anymore because it's really kind of tough for the average layperson to get a hold of the whole thing. But we're giving you the essence with some good examples. And here's the thing. These are not normally distributed. And so if you have a large sample size, such as greater than or equal to 30, and irrespective of the shape of the population distribution, which could be non-normal and sometimes severely non-normal, the mean and the standard deviation will still work out to leave the mean alone and do exactly the same thing as before. So really the bottom line is the same, but where we come in from, opens the door for non-normal distributions, provided that we have enough in our sample size, generally considered to be greater than or equal to 30. Some books or some very strange distributions need 40 or perhaps 50, but let's just go with 30 for things we're likely to see. And here's a good picture here. If the population distribution is skewed right, because of the lack of data on the right side, then we see what happens when we take sampling of size of n equals 4, and the x bars do tend to smooth out just a little bit, but it's still not very good. It's not normal. And for 15, it's better, but it's still not normal. It's still got that skew. It's getting better, but it's still got a skew to it. Now, when we get to 30, this is where the miracle occurs, and we have approximate normal distribution. Now, one could get the microscope out, magnifying glass, and see, oh yeah, there's a little bit of a skew, but it's considered to be good enough. There are actually tests for those kind of things. We're not going to worry about them. And by the time you get beyond 30, such as 80 or 100 or 1,000 or something, it's becoming pretty good approximation for a normal distribution, even if it started profoundly skewed in the beginning, or even just slightly skewed in the beginning. But as we recover what we talked about before, if you already have normality, then you can get by with tiny n's. But if you don't have normality, you need 30 in order to take care of it. If you don't have either one, call the statistician. Can't do it in this class. There are methods. We're not going to talk about them, however. But here we will either have normality or a large n, sometimes even both. So let's take a look at some examples. Mean rent paid by all tenants in a small city is $1,550. Standard deviation, 225. So the population distribution of rents, incomes, rents, stuff, economic type data, is skewed to the right. That's kind of well known. That's why the median took on prominence. But they would like to find the mean and standard deviation of X bar and describe the shape of its distribution when the sample size is 30. 30 is barely enough. And of course 100 is more than enough, but we'll take a look at both of them. So as we look at the data, X bar is the mean rent paid by a sample of 30 tenants. And the mean is not going anywhere. Don't touch it. It's already perfect. But the standard deviation changes. 30 is just enough. 29 wouldn't have been. And I have to admit, this is a slightly arbitrary number, but that's the number that's gone with. So we're going to just use that number. And 30, we're actually good to go. And the calculation is done. Notice no finite continuity correction factor or whatever. We just don't bother with that most of the time. But the standard deviation has come down from 225 down to $41 and maybe 8 cents. So even though it started off not normal, the sample size was large enough. And by the central limit theorem, things tend to go towards the center. To make a long story short, the shape of the sampling distribution of X bar is approximately normal. Good enough. And here's the picture that demonstrates that. The population distribution for the mean being 1,550 shows a lot of people paying a little less than that if you put a y-axis going this way. And less people pay more and more money, and up to the very expensive rents. Not too many people pay those, but the mean, in a skewed set of data, worked out to be 1,550. And if we start taking samples of 30 repeatedly, over and over and over, maybe you get 1,000 samples of 30, they themselves would have a mean. All those means would collect around the 1,550. There's no bias of any kind, but the standard deviation would get tighter and tighter depending on our sample size, and it's already shrunk quite a bit, down from $225 down to about $41. So now if we have 100 tenants, things just get better. It's clearly greater than 30, and it's also easy to do without a calculator, I might add, because 100, square root of 100 is 10, and dividing by 10 you can do it in your sleep. You just move that decimal over, 2250. I don't think I'd even bother with the extra zero here because that's an exact number. And that number is smaller than before. And so, yes, if the other one was normal, this one had better be normal because it's way bigger than 30. And it is approximately normal if you want to get technical about it. The mean did not change as always. And now this one's just a little bit tighter because our standard deviation has shrunk. There we have the original population non-normal distribution. And then when n equals 100, we have even a tighter standard deviation, more precise. Here's some more examples, and basically says the same thing, although there are a couple of small printing errors on this particular slide that I wasn't able to fix. So here's a real hodgepodge distribution. Yeah, Swiss cheese distribution, they used to say. So I don't know what that is. It's just something that happened. And nature does have these types of things. Yellowstone's Old Faithful is a perfect example of a bimodal distribution. But anyway, if we have a mean of mu and a standard deviation of sigma, and we have any population, and you take n greater than 30, like we just said, a miracle happens, and what we get from this is a set of numbers that works out to be pretty close to a bell curve. The greater the sample size, the better the approximation. This is an approximation if you get 30 or more. This is a bit of an extreme case. You might need 40 for something that weird, but let's not go there. Now, here's the better situation. If you start with normal, we don't really care what n is, as long as it's greater than or equal to 2. We don't need samples of size 1. They're kind of a waste of time. They're just individual values. So I'm going to go ahead and say greater than or equal to 2. But you don't have to have 30 anymore. 2 would be fine, because you're already normal. You're already at the goal. And anything you go 2 or more, it just gets better and better and better. And a little bit tighter, no matter what n is. This is not really done with any kind of scale. It's just meant to be a general review of what we just talked about. And as we've already said over and over again, the mean of the means stays as the population mean. The mean of the sample means, I should say. And this one also has a little side trip of variance. We're not very worried about it, but if you wanted to see it without the square root sign, yeah, you do have sigma squared divided by n. That is also true. We just don't pay much attention to it. And the one we do pay attention to, of course, is the one we've seen a few times already. And that would also has another name, standard error of the mean. And so a study analyzed the sleep habits of college students, and it's non-normal. You can tell by looking. The study found the mean sleep time was 6.8 hours. I would love to get that amount of sleep. I usually get 5 or so, 5.5 maybe. But you got a standard deviation of 1.4, so the data is spread out. And it's curious to see that some people get 2 hours of sleep per night, and some people get more than 11. I can't really relate to either one of those, but anyway, random samples of 100 sleep times are drawn from this population. The mean of each sample is determined. Notice when you've got a large n, we don't care if it's normal or not. The only time you care if it's normal, if you've got 30 or more, you're good. Or if it says normal, then you don't even have to worry about n. So if you've got either one of those good things happening, then you're in good shape. But if you don't have them, then you have to be careful. So the 100 rules out the need to even notice normality, and this one is clearly not normal. So we'd like to find the mean and standard deviation of the sampling distribution of the sample means. That's quite a mouthful, but that's just exactly what we've been doing. Sigma sub x bar, sigma over square root of n is what we're really looking for. So that's what we're really after. And in this case, n is greater than 30, clearly, because we got 100. Okay, so we already have been told that 6.8 was the average. And if you found all the possible x bars and averaged them up, they would be 6.8. There's no bias. That's actually a statistical word. And if there is bias, then it has to be noticed. Small bias is one thing. Large bias is completely different. Here we have no bias. The standard error of the mean is equal to the population standard deviation divided by square root of n, as we've said a few times. And since we had a standard deviation of 1.4 and we've got 100 in our sample, this makes our standard deviation very small, rather precise. So they're trying to give us a little bit of a sketch here. We don't have a Y scale, but the sample size is definitely greater than 30. 100 is greater than 30, and so we can find that the mean isn't going to change at all, but the standard deviation becomes much more precise, so to speak. So you're looking at all the x bars that come in. They should land in a very narrow range, especially with sizes of 100. And even though this is non-normal data, 100 tends to be a lot. And so, yeah, once in a while you get something that's beyond a 7 or even as low as just above a 6. That could happen, but not very likely. Here we have another example. The training heart rates of all 20-year-old athletes are normally distributed. A mean of 135 beats per minute, standard deviation of 18 beats per minute. Now, random samples of size 4. That's not 30, is it? And it's drawn from the population, and the mean of each sample is determined. So we have to get all the x bars, and we need to find the mean and the standard error of the mean of the sampling distribution, like they asked us before. Of course, I almost forgot that they did say normally distributed back there, and if you didn't see that, you could just look at the picture and figure out, yep, that's a bell curve. And yeah, so 4 is fine. You don't need 30 here. It's already normal. If it needs help to get to the goal and it's not normal, or maybe they didn't say anything, it's uncertain. Sometimes you're collecting data for the first time, you really don't know. It might be normal, might not be. Then it's always good to go with 30 or more. That way you've got more data, which is always good. But you get to 30, then you don't even care if it's normal anymore. So here, it's normal. 4 is enough. Okay, so the mean did not change, as always. Standard deviation, yeah, got a little bit smaller. Not by much. N's only 4 here, and the square root of 4 is 2. So now we're down to 9 BPM, I guess you could say, beats per minute. A little bit tighter than before, but not hugely so. So we have sigma sub x bar of 9. Was 18, now it's 9. But these are sample means with n equals 4. That's the end of our slideshow. Sorry this one got cut off into 2 parts, but that's just the breaks. And next we'll go into the last half of chapter number 7. We'll finish up some of these ideas, especially concerning population proportions